Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss atomic scattering factor. Let's begin. Atomic scattering factor, that is a ratio of the amplitude of radiations scattered from an atom to the amplitude of radiations scattered from an electron, that is known as atomic scattering factor. That is atomic scattering factor F is equal to the ratio of amplitude of radiation scattered from an atom to that of amplitude of radiation scattered from an electron. If we consider an atom having 3 electrons, that there will be an atom, that will be the nucleus of the atom, and 3 electrons are arranged inside that of atom in the cells like K, L, M. In K cell, the number of atoms are 2. L cell, the number of atoms is 1. As we taken Z is equal to 3 atomic number, which is equal to the number of electrons. So when an X-ray is incident on that of atom, X-ray is incident. Means X-ray is incident to that of electrons. Then it will be scattered. So atomic factor is the amplitude of radiation of scattered from an atom. So total amplitude of radiation from an atom is the sum of the amplitudes of scattering from these individual electrons. Let that electron amplitude of radiation will be 2, that electron having the amplitude of radiation 2, that electron also the amplitude of radiation 2. So from our formula, therefore F is equal to sum total of amplitude of radiation of that of atom 2 plus 2 plus 2 divided by 1 electron, amplitude of radiation scattered from 1 electron, which one is equal to 2. 6 divided by 2, which is equal to 3, that is Z is equal to F. So atomic number is same, is that of atomic scattering factor. That atomic scattering factor depends upon various things. The atomic scattering factor, we can also call it as form factor, atomic scattering factor or form factor. Its value depends on what be the number of electrons are present in a particular atom. Number of electrons in an atom and the distribution of electrons inside that of atom. What be the number of electrons in K cell, L cell, M cell, like that. Distribution of electrons in an atom. And also the wavelength of radiation, that wavelength indicate what be the amplitude. Wavelength of the radiation wave and the scattering angle, at which angle the amplitude of radiations are scattered. Angle of scattering of radiation wave. These are some basic points. On these points the atomic factor depends. Usually we say that the value of atomic factor F is less than that number of electrons. Usually the value of F, atomic scattering factor or form factor, is less than the number of electrons, or we can say that is the atomic number. What is the significance of that atomic scattering factor? The physical significance it indicates the measure of efficiency with which the atom scatters the incident radiation. It indicates the measure of efficiency with which the atom scatters the incident radiation. Mathematically we can construct it will be considered if F is equal to the total number of electrons that is Z present in the atom when the scattering angle is 0. Scattering angle is 0. When the scattering angle is 0, then F is equal to the total number of electrons present inside that of atom. Again, if theta is the scattering angle, if that scattering angle is greater than 0, theta is the scattering angle, means the angle is non-zero, then the value of scattering factor F is less than Z. In simple words, we can say, the atomic scattering factor F represents the total electronic charge, Z inside that of atom. F is equal to Z. Scattering factor is same as that of number of electrons present, as we look in that particular example. Now we have to derive that atomic scattering factor. Derivation: to measure the atomic scattering factor, let me consider an atom. In that of atom, the incident and reflected wave normals are at equal angles. The scattering plane or reflecting plane. To show the atomic scattering factor, we prefer an electron is at the center and the incident ray, the scattered ray makes the same angle with that of normal. Incident ray, let I cap, scattered ray S cap, with the normal, that N. It makes an angle theta here and theta there. And we consider a small volume element, the small volume element dV, small volume element. In that of small volume element, we consider the volume charge density rho r be the volume charge density, and its position the radius r and it creates an angle phi to that of normal. So the position of that small volume element is at r phi. The position of the small volume element dV, and it has small volume element dV. Then what will be the total charge inside that of small volume element? That is rho r dV. Rho r is the volume charge density, this is the volume dV, this is the total charge within dV. Since we consider X-ray is incident, one ray is incident at an electron present in the circle, then it is scattered. Another ray to that of volume element, and again it is scattered, I cap, S cap. So what be the phase difference in between these two scattered waves? From Laws equation, the phase difference that is phi, that is the phase difference in between the scattered wave at origin and the scattered wave and the small volume element dV. The phase difference phi is equal to 2 pi by lambda into path difference. So 2 pi by lambda into path difference. From that of Laplace equation, the path difference is equal to r vector dot n vector, r vector dot n vector is equal to 2 pi by lambda r vector dot n vector as r n cos phi is equal to 2 pi by lambda, the value of n is 2 sin theta, n is equal to 2 sin theta, that from Laplace equation, r 2 sin theta cos phi. Simplifying it, 4 pi by lambda r sin theta cos phi, here n is equal to 2 sin theta. Four pi by lambda sin theta is equal to m is equal to 4 pi by lambda sin theta. We have m r cos phi is the phase difference phi, and with the phase difference phi. Also the volume element dV, dV is equal to 2 pi r square sin phi d phi dr. As we know, the volume of an elementary ring of radius r sin phi width is equal to r d phi, and the thickness is equal to dr. So the volume, area into thickness, area 2 pi r sin phi, width r d theta, thickness dr, that is 2 pi r square sin phi d phi dr. Then our task is to calculating the atomic scattering factor. First we have to calculate the atomic scattering factor for that of small volume element. Then integrating that small volume element, we can get the total atomic scattering factor of that given atom. From the definition of atomic scattering factor, from the definition of atomic scattering factor, F is equal to factor df, df is equal to small atomic scattering factor, small change in atomic scattering factor there is the small change in atomic scattering factor df is equal to amplitude of radiation scattered to the charge rho r dv at the position r vector to that of amplitude of radiation by a point electron that are present at the center O. So d phi, small change in atomic scattering factor. Here the amplitude of radiation scattered to that change of that small volume rho r dv, that is given by a with the amplitude of that of radiation, and it is represented by that wave as e to the power I kx minus omega t plus phi, phase difference in between these two waves, with rho r dv. For single electron, for total electron, rho r dv is multiplied to this, divided by single electron present at the center, it is a e to the power I kx minus omega t, a e to the power I kx minus omega t, that is the wave equation. Or d phi is equal to, expanding that one, a e to the power I kx minus omega t cancel out, so another term e to the power I phi exists, so e to the power I phi rho r dv, putting the values of phi here, or d phi is equal to e to the power I value of phi m r cos phi, m r cos phi, then rho r value of dv 2 pi r square sin phi d phi dr, that is df, which one is the small change in atomic scattering factor. But calculating the total atomic scattering factor f, therefore atomic scattering factor f, that is the integration over df. So integration over df, the double integration, 1 from r stands from 0 to infinity and phi stands from 0 to pi, d phi df rho r e to the power I m r cos phi 2 pi r square sin phi d phi dr. On solving that integral, separate it as integration from 0 to pi e to the power I m r cos phi sin phi d phi into integration from r is equal to 0 to infinity, 0 to infinity, r term 0 r dr. Rho r pi r square dr. That integral is equal to 2 sin mr divided by mr into that integral 0 to infinity rho r pi r square dr. That one is the constant. When that constant is multiplied within that integral term, it will be 0 to infinity 4, there will be a term 2 pi, so 4 pi r square rho r sin mr divided by mr dr. I am taking the limit when theta approaches to 0. At that of case m approaches to 0. Then sin mr divided by mr will approach to unity. The condition for limit. Therefore, taking the limit as m tends to 0 of that atomic scattering factor f, integration from 0 to infinity 4 pi r square rho r dr, that term as 1. That integral is nothing but the total number of electrons present in that atom, which is equal to z, the atomic number of that of element, the atomic number of the element. Thus, we conclude that the atomic scattering factor small f is numerically equal to the total number of electrons Z in that atom. The atomic scattering factor is equal to the total number of electrons in that of atom, as we write it in that of physical significance of atomic scattering factor. So, here with the help of this video lecture we understand the concept of atomic scattering factor definition. Example, what are the factors affecting atomic scattering factor, physical significance of atomic scattering factor, and derivation of atomic scattering factor. And finally, we conclude that atomic scattering factor is numerically equal to the total number of electrons inside that of atom. So, with this useful and informative notes, let me wind up this session. Thank you.